Good day, everyone. We all know that population is increasing. Globally, population was projected to grow approximately from 7 billion in 2010 to 9 billion in 2050. In Philippines, based from a UN study in 2017, it is anticipated to escalate from nearly 94 million in 2010 to almost 151 million in 2050. The increase in population negatively affects the environment. There is destruction of natural habitats, production of waste, issues on land cover change, agricultural land conversion and degradation, water resource management, energy, and climate change are surfacing. These have impact on agriculture as well as food production. With population growth, there is an increased demand for food. An ADB study showed that in 2050 there should be a 70% increase in food production to address the demand on food. It was recognized that climate change is a key driver of global hunger and a main cause of severe food crisis in the world. It has largely affected agriculture in terms of the damages, especially in developing countries like ours. Projections reveal that yields of irrigated maize between 2000 and 2050 will reduce by 2 to 5%. In selected provinces in the Philippines, Lansigan and Salvacion evaluated the possible effect of climate change on corn production. They discovered using yield simulations that increase in temperature will decrease corn yields because of energy loss in maintaining respiration in plant processes. However, these predicted impacts on production would depend on the awareness and adaptation level of farmers. Potential damages of climate change in agriculture can be lessened if farmers will employ appropriate adaptation strategies. Farmers would then need information on future climate change conditions to help them decide on their production and adaptation against climate change. A study by Suarez et al. In 2018 prescribed that climate information could be used for planning and decision making for farmers to better prepare and adapt to risks and opportunities of climate change. SEAMS, or Sarai Enhanced Agricultural Monitoring System, was one of the technologies developed through Project Sarai that can serve as a decision tool for farmers and agricultural workers in advising farmers on their production. This provides relevant site-specific monitoring and forecasting information on crop growth and yield, pest and disease incidents, flood and drought occurrence, and timely crop weather advisories, specifically information on 5-month rainfall forecast. My study is on ex-ante assessment of SEAMS in selected municipalities in Occidental Mindoro, Philippines. Prior to possible deployment to interested areas who may utilize the technology, these evaluated the potential impacts of the use of SIMS in corn production in selected municipalities in the province of Occidental Mindoro, Philippines. Results of this would be helpful in determining whether it is worthy to invest in such project. Specifically, it determined the value of climate forecast for the possible deployment of the technology in the areas. This study also analyzed the costs and benefits of SIMS in corn production. It determined the willingness of municipal agriculturists and farmers to use SIMS. Lastly, identified possible factors that may affect farmers' willingness to adopt SIMS. For 3 of the top corn-producing municipalities were selected in Occidental Mindoro. These included the municipalities in red. These are Abra de Ilog, San Jose, and Santa Cruz. From each municipality, 2 barangay representatives are identified as specific sites, which are large corn-producing communities. In Abra de Ilog, barangays Armado and Cabacao were selected, barangays Barahan and Pinagturelan in Santa Cruz, and barangays Monteclaro and San Isidro and San Jose. Various data were gathered through key informant interview with municipal personnel and administration of survey with farmers. Several analyses were utilized in the assessment of the probable impacts of SEAMS in Occidental Mindoro. These include the Rapid Climate Decision Analysis, or the RCDA, Cost-Benefit Analysis, or CBA, and Logistic Regression Analysis, or the LRA. Just to give you a brief background on the farm respondents, 182 corn farmer respondents were interviewed. They have an average monthly farm income of 12,850. Their average farm area is 3.26 hectares. An approximate of 37% farmers have small farms, which according to Lauder in 2016 are about 12% in agricultural land in the world. More than 50% of the respondents have less than 4 hectares. Almost 60% of them own their farmlands, and greater than 70% have one cropping for corn. Average corn yield per cropping is 5,177 kilograms per hectare. This is greater than the national corn crop estimate of 3.17 metric tons per hectare and regional corn estimate of 3.65 metric ton per hectare in 2019. Average corn price per kilo is 13.46 pesos, which is a bit higher than the national corn price of 13.07 per kilo, but lower than the regional price of yellow corn at 14.89 pesos per kilogram last year. Rapid climate decision analysis was used to determine the value of seasonal climate forecasts in the barangays. In the illustration, you see an example of the results of the value of climate forecast in Barangay Cabacao. This method was employed to create a value on a climate-sensitive decision whether the farmer will plant or not plant given a climate condition. The value of the forecast was generated by interpolation of 100-point distribution of points derived from the decision that changed, that is, to plant or not to plant for different climate conditions. Under these climate conditions, wettest, above average, average, below average, and driest, using the collected data from each farmer leader on production, which was done through KII, the profits were calculated. Subjected to 3 different scenarios. First, as illustrated on the left side, which has an equal probability of dry and wet condition. The middle illustration, which illustrates the scenario with greater probability of wetter condition, and the rightmost illustration, which shows the greater probability of drier condition than the wet condition. RCDA showed that corn production in most of the study areas seemed to be sensitive at wetter condition. In this scenario, farmers would usually incur losses if they decide to plant corn. However, climate-smart technology such as SEAMS can provide seasonal rainfall forecasts to aid farmers in their decision-making and planning for their production. With this advent in technology, farmers can change their initially scheduled planting if they will have knowledge on the rainfall forecast. They can also decide to change the crop to plant given the information. Hence, losses shown with are shown by the negative values under the condition which has a greater probability of better condition could be avoided or lessened. Cost and benefit analysis was employed to measure the costs and benefits of SEAMS in corn production. This was conducted with reference to the intervention that is yet to be implemented in the study areas. Using a semi-structured questionnaire, municipal staff members who participated in the training on SEAMS were interviewed to identify the cost of establishing SEAMS in their area. Their perceived potential impacts or benefits of the intervention were also asked. Cost considered for setting up SEAMS in their area or municipality basically included laptop internet connection, personnel, and training. Benefits identified were savings from personnel's time monetized in terms of their salary, transportation costs of the extension worker, and damage costs in corn production. Hence, for example, the difference between the person's time monetized in terms of their salary with and without SEAMS was computed. Similarly, difference between transportation cost of the extension worker with and without SEAMS and difference between damage cost in corn production with and without SEAMS were accounted. Cost and benefit analysis of putting up SEAMS applying a discount rate of 10% for the baseline scenario as shown in the table resulted to positive net present values, benefit cost ratios greater than 1, and internal rate revenues greater than the discount rate. And these are good indicators of the feasibility of the project. The establishing SEAMS in the three municipalities is feasible and has great socioeconomic benefits at a discount rate of 10% in all areas. Looking at the willingness to adopt SEAMS by its potential users, almost staff members are willing to adopt it. They perceive that agricultural monitoring system will be helpful to them and to the farmers. As with the farmers, both for men and female farm respondents, majority of them have the same perception as that of the municipal agricultural workers. Within the last analysis, using the data from the survey, LRA was utilized to determine the possible relationship between binary response probability of the willingness of farmers to adopt SEAMS and its explanatory variables. Specifically, fractional LRA was employed since it is often used for outcomes in rates, proportions, and fractional data. This fractional response model was used to estimate the outcome of the willingness of farmers to adopt SEAMS in corn production that has a value of greater than or equal to 0 or equal to 1. On the other hand, the predictor variables used for this analysis could be subdivided into 4 categories: socio-demographic, agricultural, accessibility, and perception. The dependent variable considered was the willingness of farmers to adopt SEAMS, which is bounded between 0 and 1. Zeta was used in the analysis of the data. Among the predictor variables, age, marital status, monthly farm income, land ownership, availability of internet-capable mobile phones, access to climate information through mobile phone internet, and agricultural extension worker were discovered to be positively connected to farmers' willingness to adopt SEAMS. Farm size and access to newspaper are some of the factors which are negatively associated to the utilization of the technology. In this study, we can see that the 5-month rainfall forecast, which is one of the information SEAMS could generate and provide to farmers, can be used by them to decide when to plant and what crop to plant. Installation of SEAMS in the three municipalities is viable and beneficial to the staff members at MAU and to the farmers. And certain socio-demographic farm-related characteristics, accessibility to climate information, and sources or recognized factors related to the adoption of SEAMS at the farmers level. Thank you for listening.